Hello folks and welcome. Today we're going to talk about something called the Euler Mascheroni constant. So start with the number 1 and add to this a half and then a third and then a quarter. Keep going. A fifth and a sixth. The numbers we're adding become smaller and smaller and so contribute yet less and less to this sum. In fact, we can go on forever. A 99th, a 100th, a millionth, all the way up to infinity. Well, in fact, we can never quite get to infinity, but that's where we're headed. What we're performing here is something called a limiting sum. Now, imagine starting from 1 again, but this time add to it a quarter, and then a ninth, and then a 16th, and so on, all of the inverse square numbers. Now, the sum of these numbers up to infinity most certainly is finite. In fact, it's really cool. It's just pi squared over 6. Anyway, back to our original series. 1, a half, a third, and so on. This is called the harmonic series, and if we were to take the series up to any point and sum up to this point, the answer we get would be finite. But of course, as we've already seen, adding these numbers all the way up to infinity gives us infinity. Okay, now we need to talk about something called the logarithm. So first, let's ask ourselves a question. If we start with x, how many times do we need to multiply x by itself in order to get y? So another way of putting this is, to what power do we need to raise x in order to get y? So, for example, to get 16, we need to raise 2 to the power 4. So log base 2 of 16 is 4. Now, what do we need to raise 2.7182818459045 and so on to in order to get 5? Well, 2.7182818. 2.718, you can edit this, it'll be funny. 2.718281828459045 and so on is a number known as e. It's a very important constant in mathematics. So the logarithm to base e of 5 is what we need to raise e by in order to get 5. Now imagine a smooth, continuous way of adding up these numbers from before. Starting again from 1, but this time instead of adding to it a half and then a third and so on, let's just look at the curve 1 over x. Now you notice that this curve passes through the same points as before when x was a whole number. Okay, the first point I want to make here is that there's some mismatch between the area under the steps, or the sum of the inverse whole numbers, the harmonic series, and the area under the smooth curve, or the natural logarithm. The second point is that neither of the areas is finite. In fact, they're both infinite. But what about all those little mismatches? Well, when we sum them up, these little mismatches represent the difference between these two areas. It turns out that this sum is actually finite. So the difference between one infinity and another infinity, in this case, is equal to a finite number, which is here known as the Euler Mascheroni constant. Now, this Euler Mascheroni constant is an incredibly useful and ubiquitous number in mathematics. It's denoted by the Greek letter gamma, and the latest number of decimal places to which it's been published is a little over 119 billion.